All right, so this video is going to be about air pressure, the air pressure variable. Okay, so a couple of announcements, but make sure you bring all your notes to every class. Okay, so hopefully you have at this point memorized the 4 layers of the atmosphere. We gave you the mnemonic too many stupid tests, but I encourage you to make a naughty mnemonic if you're having trouble memorizing those. You will also need to make sure that you understand how temperature and pressure are related to each layer. Pressure is the easy one. It decreases in every layer, and we'll learn more about why that is today. But the temperature zigzags. As we leave the surface of the Earth and we go up through the troposphere, it decreases, then it increases in the stratosphere, and it decreases again in the mesosphere, and then it increases in the thermosphere. And I'm going to refer you back to those introduction notes if you have more questions on that, or come in and see your instructor. And we also talked last week about the atmosphere being a sandwich because it's heated from above by the sun and heated from below by the earth, and the atmosphere is the hamburger in between. The only thing is we have to remember the earth is the bigger heat source, so that's why that big sandwich bun is on the bottom. But today what we're also going to do is we're going to take a look at that temperature and that heat energy and how it affects air pressure and how changing those variables has effects. So first off, the air pressure book definition is the amount of force per unit area exerted by air. Because air pressure is caused by gravity, it's really a measure of the force or weight of moving air molecules. We measure it with a barometer, and 1 atmosphere at sea level is 14.7 pounds per square inch, which that's on every part of your body, and it's equalized. So you have 14.7 pounds per square inch on the front of your hand and on the back of your hand. So you don't really notice that unless the pressure gets uneven, and then you feel wind. And we'll talk about that here in a little bit. Ask your classmates about that 14.7 pounds per square inch. We don't feel it because ever since you were conceived in your mother's womb, you have felt this 14.7 pounds per square inch. And so what we do is we will unequalize that pressure and kind of have fun with a couple of students. You can ask some of your friends what that looks like. You can also ask your instructor to vacuum pack you. We literally vacuum pack some people, so it's kind of fun. You can feel that 14.7 pounds per square inch. I already mentioned this before, but gravity causes air pressure. It keeps our atmosphere here and it causes it. Smaller planets and moons don't necessarily have atmospheres because they have a lack of gravity. And so that's what makes some of the larger planets in our solar system have that really thick atmospheres because they have more gravity. So we like gravity. It makes us fall down, but it also keeps our air pressure here. We already mentioned before that altitude affects the air pressure, and that's because air pressure is affected by depth. The deeper we are, the more pressure there is because there's more stuff stacked on top of us. And so higher altitudes are like being in the shallow end of a pool. Just like in the shallow end of a pool, you don't have much water on top of you. At higher altitudes, you don't have much air on top of you. And so you have lower air pressure higher up. And so in this diagram, what you can see is at the bottom here, we have really high air pressure, but as we go up into the top of our atmosphere, we have really low air pressure. We also mentioned how thin that troposphere is because it gets smashed by all this air that's on top, and so there's more air on top of us when we're down here at the bottom near sea level than when we're up here at the top of Mount Everest. This is a good time to pause. Make sure you have blanks in your notes filled in. And even though you didn't, we're going to keep going. Okay, so what is high pressure? High pressure means there's more molecules bumping into a surface on all directions, or another way to think of it is there are more molecules stacked on top of that area. Low pressure then is less molecules bumping onto any given surface and less molecules stacked on top of an area. So that's kind of the definition of what pressure is. But right here, I would like you to pause the video for 2 reasons. One, I want you to make some hypotheses. If temperature increases, what will happen to air pressure? Will air pressure go up, stay the same, or go down? And then I want you to make another hypothesis for water. If water increases, if we put more water into the air, what will happen to air pressure? Will it go up, go down, or stay the same? After you've filled in that section of your notes, you need to stop this video and reload the other two demonstration videos. There's one called air pressure and temperature and air pressure and water vapor. You're going to watch those two videos before continuing with this one. So please pause here and load those videos to check your hypotheses. All right, now that you're back and you've watched those other videos, one rule, you cannot erase your hypothesis. We learn more from what we get wrong than from what we get right. So you're not allowed to change your hypothesis now that you know the answers. So what exactly were the answers? So let's deal with the temperature one first. The higher temperature meant less pressure. What we saw was that 2-liter bottle collapse. This is because the air is less dense and the molecules are more spread out. If the molecules are more spread out, there are fewer of them bumping against the surface, so there's less pressure. Vice versa, lower temperature means more pressure. We watched how the cool air in the room pushed in that 2-liter bottle. This is because the air here is more dense. Those molecules are more compact, and so they push in on that 2-liter bottle. In the water vapor example, what we saw was that the more water vapor there was, the less air pressure. We watched that can collapse. The less water vapor there was, the more air pressure there was. And this is because water molecules weigh less than some gases. So if we think about the water molecule itself, what we find is that water molecules have a molecular weight of about 18. So they're not very big. But if we even take trace gases like carbon dioxide and carbon monoxide, they have molecular weights more like in the 40s. So what happens is you're taking these really fluffy marshmallows of air molecules or water molecules, and you're replacing them with these big bricks of air molecules if you take water vapor out of the air. Likewise, if I put more water vapor in the air, it's like being covered in bricks and replacing those with marshmallows. The more water vapor there is in the air is like having more marshmallows. There's going to be less air pressure. The less water vapor I have in the air, there's going to be more bricks and there's going to be more air pressure. So water molecules is kind of counterintuitive. We tend to think if we put more water in the air, there should be more air pressure, but this is not the case because water is like a fluffy little marshmallow. It doesn't weigh very much, so it decreases the air pressure. Crazy, huh? All right, so to repeat, remember when we said that hot stuff and cold stuff. Now, I know you didn't say it, but say it out loud with me. Hot stuff and cold stuff, right? So if hot stuff rises and cold stuff sinks, this helps us explain convection. Warm temperatures mean the molecules spread out, and molecules spreading out are spreading out because they move more. This decreases the density, and less dense means it rises. If it's going to rise, there are fewer of them there to stack or bump onto the surface of the earth, and so warmer temperatures mean lower air pressure. Now the opposite works for colder temperatures. Colder temperatures means the molecules are going to crunch together more, they're going to move less, that increases the density, and less dense means it's going to sink. Sinking molecules means more of them bumping onto the surface and higher pressure. So wait a minute. Let's think about that. When we look at a map, how come if warm air means less pressure, we get cold, rainy days with a low pressure system? And if high pressure goes with cold air, why do we get clear, warm, sunny days? Ah, that's the rub. We're going to talk about that, and you'll be able to answer those questions by the end of this unit. But I'm sorry, I'm going to make you hold on to those right now. At this point, you should have the stuff in your note packet through page 4 filled out. So at this point, if you don't, take a break, pause it, go back, re-listen or re-watch until you get all the way through the graphic organizer on page 4 filled out. All right, so the last thing we're going to talk about that we need for air pressure is air pressure and wind. Nature does not like vacuums. It likes things to be nice and even. If you think about water, it'll spread out when you spill it, that kind of thing. Wind is a result of differences in air pressure. We mentioned this on our mapping exercise. And what we said is air would always move from areas of high pressure to areas of low pressure. And again, that's from when we made those isobars. So isobars, recall, are lines of connecting weather stations with equal pressure. And wind, we also said, would blow perpendicular to those isobars. The closer the isobars, the larger the pressure difference between those two weather stations. That's called a pressure gradient. Pressure gradients can be really wide apart. You can have really far isobars, and that would mean slower wind speeds. Closer the isobars are, the faster the wind speeds. So closer isobars are a steeper pressure gradient. You can think of that like falling down a ladder. If you fall down a ladder, you're going to fall fast, you're going to fall far, and because those rungs are close together. A not so steep pressure gradient or wide isobars are going to be like falling down the stairs in 220. They're really far apart, they're not that tall, and so you're probably going to catch yourself and not fall very far or very fast. That is like a gradual pressure gradient or isobars that are far apart. We've got a stack of marbles there on this slide so that you can think about trying to stack marbles. If you tried to stack marbles or balls of some sort, they would just roll. Molecules work the same way. Even if you had a friend hold this bottom row so that you could stack them higher, if you did that and let go, they would still roll and go farther and faster because they were stacked higher. That's the way air pressure works as well. So what causes those differences in air pressure? What causes the wind? The Earth is heated unevenly. Remember, it's not a rotisserie chicken. That means we're always going to have pressure differences. So as long as the sun shines, the wind blows. And where on Earth in general is it the hottest? That's right, the equator. Where on Earth in general is it the coldest? That's right, the poles. So what happens is we get these areas of high right here at the poles. So on your diagram on page 5, I want you to write high here at the top and high here at the bottom. And then in the box in the middle, you're going to write low. Don't worry about these guys in the center here. Okay, so we're going to write low right here. What that sets up are global wind patterns. So that's kind of the blanks that you guys are going to fill in. It sets up some global wind patterns. This is too scary for you. Don't draw this one yet. Okay, so if wind blows from high to low, you're going to draw an arrow from the pole to the equator, and then from the pole to the equator here as well. So that sets up global wind patterns that wind should blow from the poles toward the equator all the time. But you can already tell it's going to look a lot messier. It's going to look more like this one. We'll get you to how this works and why this would work this way as we continue in this unit. And for right now, though, you don't need to know this. Just know that what we've given you right now is an oversimplification. So if things seem easy, that's great. Just know that we're going to keep mashing variables to get you to this point. All right, please contact your instructor if you have any questions. Have a great day.